At 3:25 p.m., a passenger train and a freight train both left Kalamazoo, Michigan. Oh, a passenger train and a freight train both left the same place. Right now, the passenger train is 61.5 miles west of Kalamazoo, and the freight train is now 49.5 miles east of Kalamazoo. The passenger train averages 16 miles per hour faster than the freight train. What time is it now? All right, so if you're like me, I read these questions and I immediately like. First of all, I don't care. And what? What time is it right now? Well, let me look at my watch. It says like 7:07 a.m. So I get that. That's kind of a difficult thing. But I want you to realize this is just a place for us to practice and deal with complexity. Complexity is something that we always find, and there's going to be certain things that we read that we have to try and ponder and understand. So don't look at it like this is ever going to be a problem you have to deal with, but I would challenge you, you are certainly going to deal with complexity, and a way of dealing with complexity is nice. So, one of the things I'm going to do is I'm going to go to a different representation. So, the idea is I'm just organizing some known facts here. And for this situation, I know that each of these trains has two quantities, right? We have the distance traveled, the rate or speed at which you're traveling at, and the time that we're doing this. And what else do we know? We know that we have two trains. One's a freight train, so I'm going to label this freight Freight, and I'm going to label this passenger Enger. And they're going opposite directions of each other. So right now the passenger train is 61.5 miles west. So I'll write this down. The passenger train went 61.5 miles west. The freight train went 49.5 miles to the east. The the rate, let's see, the passenger train travels 16 miles per hour faster than the freight train. So because of that, I'm going to say let F equal the speed of the freight train. I should probably write that let statement. Let F be the speed of the freight train, Freigh, and that speed is expressed here in miles per hour. So the units are important to me. Now, if F is the speed of the freight train, then F plus 16 is the speed of the passenger train. Now, one of the things that I know is that the time, so t is not going to be the time that it is right now. T is going to be the, so let me write this. Let t be the hours past 3:25 p.m. So it's t is going to represent a certain amount of time past 3:25 p.m. So once I figure out what t is, the big question is what time is it right now? What time is it now? I'm going to have to take t and add 3:25 to it to figure out the current time here. But now that I know that's what t is, right? The t is the time in hours past 3:25. I can let both of these be t. So here, let's see. I do know that distance equals rate times time, right? So I know that this distance equals rate times time. But the other thing that I know is that these two distances together represent the total distance traveled. Actually, this is kind of a nice system of equations, isn't it? Wow, I didn't even. Let's take a look at that. So, distance 49.5 equals rate times time. And the other equation is 61.5 equals rate. The rate here is F plus 16 times time. Okay, so this is the thing. I gotta solve. Oh no, Let's see, this one's rate is f. There we go. Rate is f. F times t, f plus 16 times t. So this is a nice venue here. I could just solve this system of equations. Then I would definitely know what t was, and that could help me figure out the current hour. So let's see. If I choose to, I'm going to do this. I'm going to distribute t in the bottom equation. That's going to give me 61.5 equals f times t plus 16t. Now, what's sweet about that, and I didn't even plan this, what's sweet about that is I just got this expression f times t, but I happen to know what f times t is from above, from the first equation. So because of that, right, this equation's become really simplified. I can now write 61.5 is equal to 49.5 plus 16t. So I'm going to take the 61, I'm going to take 61.5, and I'm going to add to that, or subtract from it, 49.5, okay, and I get 12. So I get 12 equals 16 times t. If I divide both sides by 12, 12 divided by 16, it's a fraction, right? But it also, oh, that's nice. So it is 0.75, right? It reduces to 3/4. So this is 3/4 of an hour. And I don't have to do a lot of dimensional analysis. This is going to be easy for me to deal with. So what happens is I've gone 45 more minutes. M-U-T-E-S. So if I think about now, what is the time past 3:25 p.m.? So if I'm looking at a clock, right? If I'm looking at a clock, old school clock, here we go, a digital, not a digital clock, and this is the minute hand, it's pointing at the 25, and I'm going to add to that 45 minutes. 5 and 5 is 10, carry the 1. Oh, oh, that stinks. It's going to go around to the next hour, isn't it? Let's do it this way. 25 plus 35 minutes. So if I take 25 after 3 and I add to that 35 minutes, is going to make it 4 p.m. But I just used 35 of those minutes, so that means I got 10 more minutes left over. Um, hmm. So I think one way, so I think, let's see, 45 minus 35 is 10 minutes. So basically it's 3:25 p.m. plus 45 minutes, or 0.75 hours. Well, if I add 45 minutes to that, it's going to make, let's see, 35 minutes is going to make it 4. So I think it's 4:10 p.m. I think the time is 4:10 p.m. Why, Mr. Roberts? Well, I know that 35 minutes plus 10 minutes is 45 minutes, which is the amount of time that has elapsed. But why am I breaking it up this way? Well, because I just want to get to the next hour. And if I'm at 3:25 and I add to that 35 more minutes, that's going to make it 4 p.m., but I still have 10 minutes left over. So it should be 4:10 p.m.